There are places in our universe where the rules we know, the physics we trust, simply fall apart. These are not imaginary realms from science fiction. They are real, and we call them black holes. Imagine an object so dense, so gravitationally powerful, that nothing, not even light itself, can escape its grasp. It is a one-way trip into the unknown. We look out into the cosmos, and we see these cosmic enigmas, ultimate expressions of gravity, scattered among the galaxies, collapsed remnants of massive stars, monstrous hearts of galaxies, the frontier of our understanding. Why do we spend so much time, so much intellectual energy, trying to understand something we can never touch or visit? Because black holes are nature's most extreme laboratories. They take matter and energy and push them to their absolute limits, creating conditions we could never replicate on Earth. By studying them, we are not just learning about strange, distant objects. We probe the very fabric of space-time, the fundamental nature of gravity, Einstein's universe, the quantum realm, a cosmic stress test for all of physics. The universe doesn't owe us an easy explanation. It presents us with profound paradoxes, and it's our job to try and unravel them. Each black hole question is a question about the fundamental laws of reality. Today, we're going to the edge of knowledge. We're exploring 10 of the biggest, most mind-bending mysteries these monsters present. Buckle up your curiosity. Let's start at the very center, the heart of the black hole. Einstein's general theory of relativity tells us a story. It says that all the mass that falls into a black hole, entire stars, gas clouds, unsuspecting planets, gets crushed down to an infinitely small point with infinite density. We call this point the singularity. Whenever a physicist hears the word infinity popping out of an equation, a big red flag goes up. It's where two great pillars collide. General relativity for the very large, quantum mechanics for the very small. To describe the singularity, you need a theory that can handle both extreme gravity and quantum effects simultaneously. We don't have that theory yet. It's the holy grail of modern physics. Theories: quantum gravity, string theory, tiny vibrating strings, perhaps a fuzzball, not a point. Loop quantum gravity, space-time made of tiny, discrete chunks, preventing infinite collapse. In physics, information has a very specific meaning. The unique identity of every particle, its position, its velocity, its spin. The complete blueprint for anything that exists. A core principle of quantum mechanics is that information can never be truly destroyed. It can be scrambled, rearranged, or hidden, but conserved. Enter the black hole, the ultimate information shredder. When something falls in, it crosses the event horizon and seems gone forever. Visual hook. Book falling toward black hole. Pages turn into scrambled binary. From the outside, all we can measure is its mass, its spin, its electric charge. All the intricate details seem to be erased. Hawking's idea, the information isn't completely lost. He proposed it leaks out over time in Hawking radiation, yet his original result looked random. Another idea, the holographic principle. All the information stored on the two-dimensional event horizon, like a cosmic hard drive. Solving this paradox tests whether the laws of quantum physics are truly universal. It's a battle for the soul of physics. In 1974, Stephen Hawking made a startling prediction that turned our view of black holes upside down. Combine quantum mechanics with curved space-time, and something amazing happens. Black holes aren't completely black. They should glow faintly with Hawking radiation, caused by quantum fluctuations near the event horizon. In essence, the black hole slowly leaks energy, losing mass over immense timescales. But this glow is unbelievably faint, like trying to hear a single pin drop in the middle of a rock concert. Theories: particle-antiparticle pairs near the event horizon, quantum fluctuations of spacetime itself. One falls in, the other escapes, appearing as radiation. Confirming it would transform black holes into thermodynamic systems with temperature and entropy, linking gravity, quantum mechanics, and heat. It would be our first phenomenon requiring both relativity and quantum theory to explain. Building on Hawking radiation, we arrive at another profound question. What is the ultimate fate of a black hole? If they radiate energy, they must eventually shrink. Over mind-boggling timescales. 10 to 67 years for a solar mass black hole, perhaps $100 for supermassive ones. The universe is just 13.8 billion years old, an insignificant fraction of that time. Our best hope, primordial, microscopic black holes that could be completing their evaporation now. Theories. They vanish completely in a final, brilliant burst of gamma rays and high-energy particles. Or they leave behind tiny remnants. A remnant could be a stable, information-rich nugget of exotic matter. A final repository of everything the black hole consumed. Discovering the true end state would decide the information paradox and the ultimate conservation laws of nature. This is a classic question that has fueled countless science fiction stories. What would actually happen if you were to fall into a black hole? Einstein's general relativity says for a very large, supermassive black hole, crossing the horizon could be remarkably uneventful. Your perception of time would warp, but the crossing itself could be smooth. Quantum mechanics offers a different picture. To solve the information paradox, some propose a firewall, a seething, high-energy wall at the horizon. As soon as you touch it, you'd be incinerated. But that violates Einstein's principle that a freely falling observer feels nothing at the horizon. For smaller, stellar mass black holes, the debate is academic. Long before the horizon, you'd feel intense tidal forces, stretching vertically and squeezing horizontally. This is called spaghettification. Knowing which scenario is correct, gentle passage, firewall, or spaghettification, would force us to reconcile Einstein's smooth geometry with the chaotic quantum world. It would reshape our view of space-time itself. The idea of a wormhole, a theoretical tunnel through space-time, is one of the most tantalizing concepts in physics. Einstein's equations allow them as exotic solutions. The Einstein-Rosen bridge connects a black hole to a white hole. But classic ER bridges are incredibly unstable. They collapse before even a photon can pass. Traversable wormholes would require exotic matter with negative energy and negative pressure, never observed in needed quantities. Modern ideas link gravity and quantum mechanics. The EPR conjecture suggests entangled black holes might be joined by non-traversable wormholes. If black holes were wormhole entrances, they wouldn't be safe subways. They'd likely be unstable and deadly. Yet their existence would change our cosmic map, revealing a more complex, interconnected space-time topology, perhaps even hidden dimensions. It would show a deep link between space-time geometry and quantum weirdness. Giants of the dawn. How did supermassive black holes form so quickly? When we look back in time, less than 1 billion years after the Big Bang, we see something puzzling. Fully formed galaxies with supermassive black holes, some already billions of solar masses. Standard growth is slow, capped by the Eddington limit. Radiation pushes gas away, choking off the feed. Theories: direct collapse, enormous primordial gas clouds collapsing into massive seed black holes, or exceptionally massive first stars whose collapse produced larger than usual seeds. Supermassive black holes are active architects. Their energy heats and blows out gas, regulating star formation. Understanding their rapid growth fills a missing chapter in cosmic evolution. It explains the intimate dance between galaxies and the monsters at their cores. Is bigger always better? Do black holes have a maximum size? From Sagittarius, A to M87 to TON 618, nearly 66 billion solar masses. On one hand, there's no known law imposing a hard upper limit. If there's food, a black hole can keep growing, eating stars, swallowing gas, merging with others. But radiation pressure and feedback can blow gas away, starving growth. On the largest scales, cosmic expansion spreads potential fuel too far for isolated giants. Determining whether a true maximum exists reveals the balance between local gravity and the universe's expansion. Finding ultramassive outliers could imply new early growth mechanisms or challenge galaxy formation models. It's a question about the ultimate balance of power in the cosmos. The smallest monsters. Can microscopic black holes exist? Could black holes exist with the mass of a mountain, a car, or even a proton? Hypothetical primordial black holes, forged in the extreme early universe. We haven't found any. They'd be incredibly hard to detect. A mountain mass black hole would be smaller than a proton. Best hope, catch their final Hawking evaporation, a detectable flash of gamma rays. Speculative theories suggest creation in high-energy collisions if extra dimensions make gravity stronger at small scales, but LHC searches have found no evidence so far. Discovering even one would be world-changing, a window into Big Bang physics and possibly proof of extra dimensions. These tiny monsters could connect the infinitely large with the infinitesimally small. The fabric of reality. Is space-time different inside a black hole? We speak of a smooth fabric, but like cloth, up close it may be threads. Could space-time be quantized? Inside the event horizon, space and time swap roles. The inward direction is as inevitable as time's arrow outside. Loop quantum gravity, smallest area and volume, no point singularity, a Planck star at maximum curvature. String theory, space and time may dissolve into more fundamental vibrating strings. Is reality analog or digital, smooth or grainy? Learning the true interior could resolve the singularity, the information paradox, providing a unified description of physical laws. At the breaking point of space-time, we may finally learn what it's truly made of. Section 12. Conclusion. Why the darkness matters. So we've journeyed to the edge of understanding, peering into 10 of the deepest mysteries the universe has to offer. Black holes matter because they are the ultimate testing ground for the laws of nature, where general relativity and quantum mechanics clash. A theory of quantum gravity for the singularity could describe the Big Bang. Resolving the information paradox would redefine reality, time, and causality. Detecting Hawking radiation would confirm gravity's link to thermodynamics. Each answer is a key unlocking new laws, new principles, maybe even new dimensions. They remind us the universe is more clever, more strange, and more magnificent than we can imagine. The quest to understand them is a testament to the power of mathematics, observation, and an insatiable desire to know. Thank you for joining me on this journey into the darkness. I hope it has illuminated your curiosity. If you enjoyed this exploration of the cosmic frontier, please hit that like button and subscribe to the channel for more journeys into the universe. And let me know in the comments below. What great mystery of the cosmos do you want to explore next? Keep looking up, like and subscribe. Put what you want to see next in the comments below.